Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. So in my channel, I deal with the different aspects of mathematics, physics, chemistry, and biology. And today I'm going to look at a concept under the radioactive decay, that is the concept of a spontaneous fission. Now, we had earlier mentioned this specific concept of a fission, and we said that a fission basically refers to, or as I can roughly define it, refers to the fragmentation or rather splitting of the atomic nuclei and to form daughter nucleides, and this is going to result in the release of energy and other related particles, which we had said to be part of the radioactive decay. So basically, fission refers to the concept of splitting, and this concept of splitting is of course initiated by either the bombardment with a neutron or other processes which of course are going to result in a state of instability in the nucleus. So we're going to look at specific examples, and of course from this aspect of what we refer to as spontaneous, we have said that one of the aspects or the characteristic of a radioactive process is that it is a spontaneous process, which means it's not initiated by an external factor. So therefore we are going to consider this kind of a spontaneous fission from that particular perspective in our discussion for today. Now, in our analysis of the trends of course, various trends across the periodic table, especially for the radioactive elements, we're going to see that the ratio between the neutrons and the protons, of course, are going to cause some sense of stability in the nucleus. And as we said, this is going to be dictated due to the fact that there is going to be some short range and of course nuclear short range forces which are going to be experienced within the nucleus, and therefore they are going to determine the nature of the stability of the nucleus. So an increasing number of Z, as we said, is going to result in the formation. Of course, we have to see that Z is the number of the protons in the nucleus. So therefore, an increase in the number of the protons in the nucleus, which we say are positively charged, are going to result in an increase in charge. And of course, for larger values of this particular value for Z, we're going to see that there's a particular trend that's going to be assumed, whereby those specific nucleus which are going to have an increment in the number of Z are going to be unstable. And of course, this is going to be reflected especially for the category of radioactive elements, which of course are going to be having increasing values of Z, and therefore resulting in the formation of instability. So these radioactive elements are going to undergo spontaneous fission, and this is going to result in the formation of two nuclides and perhaps two or more nuclides, and release of some of the neutrons which are going to be involved in this specific process. So to try and pinpoint this specific trend across the periodic table, we're going to consider the mass numbers, as I said, and of course an increment in the number of Z, of course, is going to dictate that basically the mass number is going to, of course, be affected in this particular case. So therefore, spontaneous fission is going to be only possible for atomic nucleus whose values are going to be greater than 100. So this is, of course, theoretically possible, but practically we're going to see that there's going to be a specific trend across the periodic table, whereby we're going to see that this can be assumed to be true for elements which are near this specific element that you call, this is going to be ruthenium, which of course is going to have a mass number of 101 and 104. So this is a theoretical aspect whereby we are going to expect this particular range of numbers that have got a mass of greater than 100 to be experiencing this process of spontaneous fission. But in practice, we're going to see that in the trends across the periodic table, this is going to be possible for atomic masses which are above this particular element, which is thorium. So we had mentioned earlier that thorium is one of the natural radioactive process, particles, which is going to have a mass number of 232 and an atomic number of 90. So basically, this is going to create a distinction between what we expect to be a result in this, of course, a theoretical aspect and the practical aspect from the trends that we have witnessed across the periodic table. So therefore, we're going to expect the elements which are having a mass number above thorium to undergo this specific process of spontaneous fission. So, so this kind of elements are going to be, of course, the ones that are going to fall under the class of actinide series. So we can be able to mention a few of these, perhaps elements like Mendelevium. We're going to have elements like Lawrencium, and some elements like, of course, which are going to be the transactinide elements like Rutherfordium are going to fall under this category. For instance, we can be able to just illustrate that one. This is going to be Rutherfordium 267. So this is around 267, if I'm correct for that, and this is going to be 104. So if you try to look at this, of course, for this element, Rutherfordium, Mendelevium is going to have a mass number of so this one is going to be 258, so it's going to be above this specific case. So practically we expect it to undergo this specific process of spontaneous fission. And of course I've mentioned the concept of Lawrencium. Lawrencium is going to have a mass number of 262, so we can be able to give it as such. So therefore it's also going to be expected to undergo this particular process of spontaneous fission. So therefore, as we have already been doing, we're going to have a general illustration for this specific process of a spontaneous fission, where we have said that basically the process of a spontaneous fission involves the reductive decay process, where a heavier atomic nucleus is going to split into two or more lighter nucleus or nuclei. And we can be able to illustrate that one using our general example for X that is going to consist of the mass number and the atomic number as such. And in this case, we're going to have, of course, a delta nuclei represented using that particular notation for. And if this Z, but this Z is different from this one. It's just an alphabetical letter to denote, or perhaps I can just give it as even K. K does not. So it's going to be a general illustration for that, which is going to have Z2, and of course this is going to be mass given as A. So therefore this is going to be accompanied by the release of the neutrons, which are going to be referred to as V. So V is going to represent the number of neutrons which are going to be released or accompanying this specific process of a spontaneous fission. So we can be able to look at a few examples. As we said, an increase in the number of the atomic, or rather this particular number for Z is going to result in the process of spontaneous fission, and this basically is due to the fact that these elements are going to be unstable. So therefore we say that as the number or the value of Z increases, the sense of instability is going to be more pronounced, and therefore we are going to expect these specific elements to undergo spontaneous fission within a relatively shorter time, and that one of course is going to have an impact on their half-life. So for instance, if we have an element like plutonium, this is going to be 240, thereby it is above this specific element for thorium that we had expected to be practically involved in this process of a spontaneous fission. So if we have plutonium 94, we can be able to see that this half-life for this specific radioisotope is going to be given as 10, 11 years. So we can see in order of magnitude, this is a very long period of time. But if we have an element like, this is a Cm, which is cesium, so we are going to have it given as 44, and then we're going to have this one as 96. So this is going to have 1, 4, and then we're going to have this one 10 to 7 years. And then lastly, we can be able to compare this one with the Californium, which is going to be given as such. So this is 98, and this is 252. And the half-life for this one is going to be 66 years. So in a sense, if you try to consider this specific range of values, we're seeing that it falls under the category of a range of elements which are going to undergo spontaneous fission, as we had mentioned. So this is from the mass of elements which are above, of course, thorium, as I had mentioned. And of course, we're saying that this specific range of values for the mass number falls under that category. But if you try to see the value of Z from 94, 96, 98, it is increasing in its specific trend. And if you try to look at the concept of the half-life for these specific elements, this is the 10 to power 11, 10 to 7, and 66 years. So generally, there's a decrease in the trend of a half-life that we're trying to witness for these specific elements. So therefore, as the number of the mass increases, the half-life is going to decrease, and this is going to depict an aspect of a decrease in, of course, half-life, and therefore increase in this in stability due to increase in the number of Z. So therefore, that one is going to give us a clue on the aspect of a spontaneous fission and a range of elements which are going to undergo this specific process in order to attain stability in the radioactive decay processes. So this, together with other videos, are going to assist us understand better these various aspects of radioactivity. And check in our description boxes for various links of other videos which are going to assist us understand the same. So that is it for now, guys. Bye, God bless.